Okay. Good morning, everyone. Let's get started. So first of all, please start. Another reminder. So having started the SVM homework, we started right now. I think our homework is due before the Thanksgiving, so really don't want you guys to spend extra time in Thanksgiving. And if you need some help, want some discussion, please come to please leverage the office hour. Okay. And right now we feel like the office hours are becoming empty again. Okay. So in the last lecture, we talked about the definition of artificial neural networks, right? And how do we compute the prediction given the neural network parameters and given the input, right? So basically, you can view neural network is a graph, a cyclic directed graph, right? We compute the neurons layer by layer until you start from input layer. We compute neurons layer by layer until we get to the output neuron as our prediction, right? And then we talk about how do we train the neural network, right? The training of the neural network amounts to estimating the weights on the edges connecting different neurons, right? So if you can think about a neural network is something like that, right? So this is the neurons, this is neurons, this is neurons, right? So one layer of neurons are connecting to the neurons in the next layer, so something like that, right? And also maybe this is a input layer, right? And the input neurons will be the input features. So on any edge, there is associated edge weight, right? Those are the neural network weights. We want to estimate those weights from the data. To do that, we can construct a loss function, right? You go over a set of training examples, right? For each training example, you use your neural network to compute the prediction and then calculate loss with respect to the ground truth prediction, right? So, and then from that, you got the loss function. Then our goal is to minimize this loss function to find out the optimal weight parameters. So the whole training procedure can be resolved by applying the stochastic gradient descent framework. We discussed it for other learning algorithms before, right? So given the training set, we first initialize the parameters of the neural network. Then we go through the data set for big T epochs. And inside each epoch, we first randomly shuffle the training set, then go through every training example, right, one by one, right? And for every training example, right, we treat this example as the entire data set, then compute the gradient of the loss on this particular example, right? So we use that gradient as the stochastic gradient. Right? We just update the model parameters using stochastic gradient descent. And of course, we need to carefully choose the step size gamma t, right? At least it should satisfy two conditions we discussed before, right? To ensure the convergence to some local minimum. Right? So those framework is pretty the same as we did for training least mean square regression or SVM, right? However, the problem has yet been resolved, right? The key step is actually the computation of the gradient of the loss, right? For any randomly selected example, right? So as we discussed in the last lecture, right? Although neural network has some kind of analytical form to calculate the prediction given the input and also model parameters, right? But the model neural network has many parameters, right? So like it's not surprising that you got like hundreds of layers, right? And each layer might contain like 100 neurons. So in total, you got like 1 million parameters. That's very, very common. So if you just try to manually derive the gradient of your loss with respect to every edge weight, that will be extremely tedious, right? And not to mention how to compute that, right? Imagine that you're gonna do a for loop over 1 million times, right? To calculate gradient with respect to every parameter, right? That is very, very costly. So to efficiently apply the stochastic gradient descent for neural network training, a key step, right, will be efficiently compute the loss gradient for any training example, right? So that it is the core technique or the most popular technique in neural network, which is called backpropagation. Okay, so before we talked about the backpropagation, right? So I'm gonna repeat this setting, right? The whole setting of the training procedure is as follows. So we have a neural network. We have defined the structure of the neural network, including how many layers, how many neurons per layer, which particular activation function you choose, and also how do you initialize the neural network parameters, right? So with that, we can make a prediction from the input. And then we have defined a loss function over every training example, right? Probably just a square loss, or perhaps a square loss plus some regularizer, right? And then our goal is that under the stochastic gradient descent framework, every time we randomly pick up an example, right? This example either can be randomly selected or just randomly shuffle the example and look at them one by one, right? And then you want to take the gradient of the loss on those randomly select example, right? And use this stochastic gradient to update model parameters. That is our setting. Right? So any questions so far? Everyone is comfortable. Everyone is on the same page, right? I'm just repeating or summarizing what we have discussed in the last lecture. Okay, great. So how do we efficiently compute the loss, the gradient of the loss of the neural network, right? So we're gonna leverage the chain rule, right? In the end, you will see that backpropagation is in essence a smart usage of the chain rule, right? I believe everyone is familiar with chain rule, right? You should learn that during your calculus 1, right? So let us briefly review chain rule, right? But here, we're gonna use some graphical illustration of the chain rule because that will be very, very helpful and important for us to understand how backpropagation works, okay? So basically, chain rule is a rule to compute gradient or derivatives for composite functions, right? So let us consider a case that z is a function of y, right? And y is a function of x, right? So it's typically a composite function, right? And then we know that z must be a function of x as well. The problem is how do we compute partial z or partial x, right? The partial gradient of z with respect to x, right? So we know that according to chain rule, partial z over partial x equals to partial z over partial y times partial y over partial x. Right? This is just chain rule. Okay. So we can represent this computation through a dependency graph, right? So we got 3 variables, x, y, z. So each variable is represented by a node in this graph, right? And then if there is a direct functional relationship, then we draw an edge between 2 nodes, right? So we say z is a function of y. That means we have an edge starting from y pointing to z, right? So z is a function of y. So in this graph, you can okay, in this graph, z is a parent of y, right? There's a connection. There's an edge connecting from y to z, right? And similarly, y is a function of x, then we draw an edge from x to y, right? And the direction of the edge, this arrow, just indicate who is the function of whom, right? So the parent is a function of the children, right? And then we construct this dependency graph. And then on each edge, we're gonna compute a partial derivative. That is the partial parent node over partial child node, right? So on this edge, for example, on this edge, right? Because it indicates z is a function of y, right? We're gonna compute the partial z over partial y, right? And on this edge, right, y is a function of x, right? Y is parent, x is child. So on this edge, we're gonna compute partial y over partial x. And then if we want to compute the partial derivative between arbitrary two nodes, right? That is partial z over partial x. Graphically, we first find a path, right? Find all the path from x to z, right? In this graph, there's only one path, right? X go to y, y go to z, right? And then we just multiply all the partial derivatives along the path. So we have one path and we multiply all the partial derivatives along the path. That will include two partial derivatives, partial z over partial y times partial y over partial x. Then we get our result, partial z over partial x. Okay. If we have multiple paths, what will we do? Yes. Yes, exactly, right? So, for example, if there is another variable alpha, z is function of alpha, and alpha is function of x, right? So we got two paths from x to z, right? So that means partial z over partial x will be the summation of the product of the derivatives along the two paths, right? So here we know on this edge will be partial z over partial alpha, and this edge will partial alpha over partial z. So in addition to the product along this path, we're gonna add a product along another path, which is partial z over partial alpha times partial alpha over partial x. Okay. So this graphical illustration obviously is even more intuitive, right? Any questions so far? I guess everyone is comfortable with that, right? Okay. So yeah, actually this is a immediate instance of multiple graphs, right? So if z is a function of y1 and y2, and both y1 and y2 are functions of x, if you want to compute partial z over partial x, you're gonna enumerate two passes, right? So actually it's the same instance as we just mentioned, right? You just multiply the partial derivatives along each path, right? And add them together. So partial z over partial y1 times partial y1 or partial x is first product, plus the product along the second path, partial z over partial y2 plus partial y2 or partial x, right? So in general, if z is a function of n variables, y1 to yn, and each yi is a function of x, then when we compute partial z or partial x, right, we got n paths from x to z, right? And then you just compute the product of the partial derivative along each path and add them together, right? Which is here. Okay, so any questions so far? So next, we're going to use this graphical representation and chain rule to do the gradient calculation of the neural network's loss, right? So suppose for a particular input, right, x1, x2. Remember, x0 here is 1, and z0 here is 1, right? It's constant, right? So through some forward pass, as we discussed in the last lecture, we compute the prediction y, right? So we're gonna first compute z1 and z2, and computation of z1 and z2 is a weighted combination of the incoming neurons, right? And then we do a nonlinear activation function. And once we compute z1, z2, and we combine z0 to compute the output y, right? In the output layer, we just do a linear combination. Right? There's no nonlinear activation function. Right? So we know that the output y is a function, a composite function of all the edge weights here, right? And also the inputs. Right? So, and then we use this output to compute loss, right? And the y star is the ground truth. Then our goal is to compute the partial derivative of loss with respect to area edge weight, right? So here edge weight, we have like two types of notations. One is WIGH, just means, remember WIGH. H means the target layer, right? So there's one edge, right? Connecting what the layer it connects to, right? And I is the source node in the previous layer, and G is the target node in the target layer H, right? For example, if you look at here, right? So this is an edge point to the hidden layer. So the superscript is H, right? And the source node is X2. So the index of source node is 2. And the target node is Z2. The index of target node is 2 as well. So we denote it as this weight as W22H, right? So it's just the notation. We just explained it before, but we just want to re-explain it, to avoid you guys from being confused, right? So like this one, right? The weight is on this edge. Again, this edge points to the hidden layer, so the superscript is still H, right? And the source node index is 0, right? X0, and target node index is 1, so the index is 1. So this edge width is denoted by W01H. Okay. So our goal is to compute the partial derivative of the loss with respect to every edge weight, either on on the edges connecting the input layer and hidden layer, and on the weights on the edges connecting between the hidden layer to the output layer. So that will include W010, W110, and W21. Right? Is everyone clear about the setting? So now let's see how to compute them. Right? Let us start with this guy. Right? So if we want to compute partial L, the loss function, with respect to W010, right? How can we do that? So we can apply the chain rule, right? Remember, L is function Y. Right? Y is function of W010, right? Remember, Y is computed by a linear combination of the neurons in the second last layer, Z0, Z1, Z2, right? So then we apply the chain rule. We get that partial L over partial W010 equals to partial L over partial Y, then times partial Y over partial W010. Right? So partial L over partial Y is straightforward. If we use square loss, right? We take the partial derivative with respect to Y, which is simply difference between Y and Y star, right? And the word is partial Y over partial W010, which is simply 1, right? Because Y is just the linear function of W010. Right? So we got first result. Right? So now let us move to the next attribute, W110, which on the edge connecting Z1 in the hidden layer and Y in output layer. Again, we use the chain rule, right? So we can first compute partial L over partial Y, and then partial Y over partial W110. So you can see there is some like redundancy, right? When we compute partial L over partial W010, we have already computed partial L over partial Y, right? So that means we shouldn't recalculate, right? We should catch it, right? So what we really need to do, like is something brand new, is that we have to compute partial Y over partial W110, right? What is that? It's just Z1, right? Because the coefficient of W110 is just Z1, namely the input neuron, right? So we just read out partial L or partial Y, which has already been computed in the previous step, right? And we just need to calculate something new, which is partial Y over partial W110, which is simply Z1. Right? So get the second result. So it looks straightforward, right? Okay, yeah. So don't feel boring, right? We're gonna get to a more interesting part in a minute. As we just mentioned, right? Partial L of partial Y have already been computed for the previous case, so we need to catch to speed up. Right? So you see that the key idea of backpropagation is to smartly catch the previous results, so you don't need to recompute them again. So now we can follow the same procedure to compute partial L or partial W210. Right? So now let us look at a little bit more complex case. So what if we want to compute partial L over partial W22H, which is on the edge connecting X2 and Z2 in a hidden layer. Right? Run this. Again, we're going to use a chain rule. Right? L partial L over partial Y times partial Y over partial W22H. Now the question is, how do we compute this guy? We need to look at how Y is dependent on W22H, right? Actually, from this figure, right, from this neural network graph, it has already shown the function dependencies, right? So if we want to compute partial Y over partial W22H, we know that Y is a direct function of Z0, Z1, and Z2, right? Y has a direct functional relationship from Z with Z0, Z1, Z2. Why? Because here, right? So we can apply the chain rule in the sense that we can first compute partial Y over partial Z0, then partial Z0 over partial W22H, plus partial Y over partial Z1 times partial Z1 over partial W22H, and partial Y over partial Z2 times partial Z2 over partial W22H, right? It makes sense, right? So now I want to ask, what is the partial derivative of Z0 and Z1 with respect to W22H? 0, right? Why? Because Z0 is constant 1. Z1, the computation of Z1 has nothing to do with W22H, right? So Z1 is computed from X0, X1, X2, and all the edge weights on edges pointing to Z1, right? But W22H is not on any of those edges. So Z1 has nothing to do with W22H, right? If you don't feel comfortable, you can try to write it out, right? It's a activation function of the linear combination of the input neurons x0, x1, right? So this edge weight should be denoted by 1, 1, h, x1, and this edge weight should be noted by 2, 2, 1, h, x2, right? So you can see that it doesn't contain W22H at all. So partial Z2, partial Z1 over partial W22H is simply 0 as well. The answer is 0 because Z0 and Z1 do not depend on W22H, right? So that means there is only a Z2 who depends on W22H. Right? Z2 actually is the target node, the edge that contains W22H points to. Right? So then we got the results, right? So we got results, partial L over partial W22H equals to partial L over partial Y, then partial Y over partial Z2, right? And then partial Z2 over partial W22H. Does it make sense? Okay. So let us map this guy to the graphical illustration of chain rule we have just discussed. Right? So we know that W22H only relates to Z2, right? And now, if you look at Z2 and how it connects to the output Y and the loss function value, right? So that means, okay, we can draw a path, right, from Z2 all the way up to the output neuron to the loss function value, right? So there's only one path. Right? There's only one path. You can try to find out. There's no other way, like you're starting from Z2, another route that goes to Y, right? There was only one path. So as we mentioned, to apply the chain rule, we just multiply the partial derivatives along that path. Right? So the partial derivative on this edge will be partial L or partial Y, right? And the partial derivative on this edge, which connects Z2 to Y, will be partial Y over partial Z2, right? And finally, we're going to compute partial Z2 over partial W22H, right? You just multiply them together, you get the results. Does it make sense? Right? I'm just talking about, like, if you just say you apply the chain rule algebraically, okay, you'll find out, okay, you do the full expansion, right? You find out, okay, this guy is simply 0, right? You end up with this guy, right? But this guy can be immediately read out by looking at the graph structure. Right? Just look at the target node, the edge containing W22H points to, right, Z2, right? And look at all the paths from Z2 to the output neuron Y, right? And here, there's only one path. So that means if you want to compute the partial derivative with respect to this W22H, you just multiply the partial derivatives along that path, right? And of course, you need to multiply this partial derivative at the end. That is partial Z2 over partial W22H, right? This is a very simple case. But if you have multiple paths, right? If you have multiple paths from Z2 to Y, of course, you need to multiply the partial derivatives along every path and add them together by following the chain. Does it make sense? Any question? Okay. So before we move to our more complex things, later we'll see that what if some node connects to the if you want to find a path from some root, some node to the output neuron, there are multiple ways. We're gonna showcase such kind of example, and you'll see that actually in practice, those can be quite complex, but they always follow this simple graphical representation of the chain rule. Right? But before we do that, right, you just want to look at a little bit details about how to compute the partial derivative, right, in this product. Right? So partial L over partial Y here is Y minus Y star, right, which is straightforward, right? And then partial Y over partial Z2, right? This guy, we know that Y is a simple linearly combination of the neurons in the hidden layer, right? So partial Y over partial Z2, which is relatively simple, is just the edge weight, corresponding edge weight, which is W210, right? Here, right? And then how to compute partial Z2, the third term, right? Partial Z2 over partial W22H. So first, how is Z2 computed? Right? For any neurons in the hidden layer, right? In the middle. In addition to a linear combination, we also do a nonlinear activation function. Right? This is how we compute Z2. Right? We're going to first do a linear combination of the incoming neurons, right? And they're weighted by the weights on the edges, right? And then we'll apply nonlinear activation function, right? So to compute the partial Z2 over partial W22H, we'll again apply a chain rule because this is essentially a composite of linear function and a nonlinear activation function, right? Well, we can again apply the chain rule, right? So we just will the input to this nonlinear activation function as a whole, right? We call it S, right? Then partial Z2 over partial W22H is to compute partial activation function sigma over partial S, right? And then partial S over partial W22H, right? So what is partial S over partial W22H? X2, right? Because S is just a linear combination. It's just the expression inside the parentheses, right? So the only step, the remaining step is compute partial activation function with respect to its input, right? So it really depends on how you choose the activation function. Different activation function will give you different partial derivatives. So here, for example, sigmoid function, if you use the rectified linear, right, it's max 0s, it's called rectified linear function. Well, you can use a subderivative, right, or subgradient. We have discussed, in the hinge laws, right? So here I want to showcase this guy. Right? If you use sigmoid activation function, right, what is the partial derivative? Right? I'm doing this is to help your homework. And I also want to show you a well-known result. So let us assume our activation function is a sigmoid function, which is 1 over 1 minus e to the power of minus s. Right? So if you want to compute, let me use partial derivative of sigma over partial s, right? So just apply the rule, right? So this guy will be, so this one is 1 plus e to the minus s to the power of minus 1, right? So just apply the rule, right? So you move the exponent in front of it, and the 1 plus e to the minus s and minus 2, right? And then you need to take the partial derivative over e to the power of minus s, which is simply e to the power of minus s, and then minus, right? Well, I'm actually applying the chain rule again, right? This is a relatively straightforward. I'm not gonna emphasize again, right? So I have a 2 minus sign here, right? It just canceled. So now eventually we got e to the minus s over 1 plus e to the minus s and square, right? So this is a result of partial sigmoid function or partial input s, right? So, but if you can make a smart observation, there's very interesting result, right? So if we can write out this square, right? So this essentially equals to e to the minus s 1 plus e to the minus s times 1 over 1 plus e to the minus s, right? I just write 1 plus e to the minus s squared as 1 plus e to the minus s multiply itself, right? So what is this guy? Right, it is a, look at here, right? It is a sigma s itself, right? And what is this guy? Yeah, 1 minus sigma s itself, right? This is a very well-known result, right? So the derivative of the sigma function is sigma times 1 minus sigma. So it's non-negative, right? Sigma function itself is between 0 and 1, right? So 1 minus sigma will be between 0 and 1 as well. So their product will be always non-negative. That means this function is monotonically increasing, right? Okay, just to give you the result, right? Once, for example, if you're asked to implement a neural network, right, with sigma activation function, right, you don't need to implement this tedious stuff, right? You just implement your own sigmoid, and then you use your sigmoid implementation to implement its derivative. Any questions so far? Okay. So then we can get our result, right? By putting all those together, right? Partial Z2 over partial W2 to H, according to the chain rule, is partial sigmoid over partial S times partial S over partial W2 to H, which is X2, right? And partial sigma over partial S, when we choose sigma activation function as an example, will be partial S over partial 1 minus X and multiply X2, right? This final give us gives the result, right? And following the same procedure, you can compute partial L over any other edge weight, right? Like W01H, W2, W02H, and so on, right? They basically follow the same procedure, except that you're going to change the numbers, right? So now, going back to the graphical illustration of the chain rule, right? So want to leverage the graphic structure of the neural network to directly finish some kind of computation. So as we just mentioned, if you want to compute partial derivative of L with respect to any edge weight, right? So first look at which node or neuron this edge points to. And here, for W2 to H, the edge points to Z2, right? Here, the yellow circle, right? Yellow shaded one. Then we just look at all the paths starting from Z2 and then arrive at the output neuron Y. Okay. Then to compute partial L over this edge weight, right? We multiply the partial derivatives along each path and add them together, right? And again, because in this case, from Z2 to Y, there's only one path. We actually only need to multiply the partial derivative along that path, and then multiply with partial Z2 over partial W2 to H. You get a result. And what about the general case? Let us formalize this to a more general case. In general, if you want to compute partial L over an edge weight denoted by W, M, and H. So M and H just means you connect ZM in the previous layer, H minus 1, to Zn in the target layer H, right? So this is the edge where W, M, and H stays on, right? So if you want to compute, so suppose this is Y, right? So if you want to compute the loss function with respect to this particular edge weight, you have to look at the target node, Z and H, and draw all the paths to the root node or to the output neuron Y, right? And then you multiply the partial derivatives along each path, then add them together, then multiply partial Z and H over partial W, M, and H. This is the general idea. Does it make sense? Right? We're going to look into the formal description of that. Everyone's good, right? Okay. So here's our general recipe, right? To apply the chain rule, right? To compute every partial L over partial W, M, and H, right? Again, let me emphasize the notation here. H is the layer number where the edge points to, right? Which is target layer number. So W, M, and H connects mth node in layer H minus 1, which is here, right? To the nth node in layer H, which is here, right? And W, M, and H is on edge connecting these two nodes, right? And for convenience, let us denote the input layer as layer 0. Okay? And if the output layer is layer T, then we index the output neuron as Z1T, right? So we use index 1 to index the output neuron. And in general, how do we compute this partial derivative? Right? Here's the procedure. First, we initialize the result to be 0. Then we find all the paths from the target node Z and H here to the output node Y. And then we enumerate every path S, right? And for each node Z in S, we compute the partial derivative of this parent, namely, what's the edge pointing, starting from Z pointing to, right? Over Z, right? If you reach the output node Y, then you compute partial L or partial Y. Then you multiply all the partial derivatives along the path S to obtain GS, right? That means the gradient along that path. Then you multiply the partial derivative at the end node, Z and H, which is partial Z and H over this particular edge weight. Right? You add this to the current result. Then you look at the next path, and then you compute all the partial derivatives along another path, multiply partial Z and H over partial W, M, and H again, right? Add to the current result. Right? You just add all the results over all the passes, right? You finally get the partial derivative with respect to W, M, and H. Right? To give a concrete example, right? Let us randomly draw some example, right? So suppose this is Y. Right? I just look at Z and H. How many passes connect ZNH to Y, right? So suppose there are 3 passes, and I'm going to just random draw, right? And here I'll just randomly represent those nodes, right? So let me denote it by Z0, Z1, and Z2. Right? So suppose this is our neural network, right? So we know that the output neuron will be fed into the loss function. So we got loss function value L, right? So if we want to compute partial L over partial W, M, and H following this procedure, what shall we do? We first look at the target node this edge points to, right? Which is ZNH. We look for all the passes from ZNH to the output neuron Y, right? How many passes do we have? 3 passes, right? So let us look at the passes one by one, right? We just want to compute the partial derivative over all the passes. Right? For every passes, and see for this pass, we multiply the partial derivatives along that path, right? Which is for the Y, we have a partial L over partial Y, right? Then we'll move to Z0. Then we'll compute partial Y over partial Z0. Why? Because Y is the parent of Z0, right? And then you move from Z0 to Z2. So now Z2 becomes the parent. So we compute partial Z0 over partial Z2. Right? Then you move from Z2 to ZNH. So we compute partial Z2 over partial ZNH. Right? You finish computation and the multiplication of partial derivative along the first pass, right? And then don't forget, you need to multiply the partial derivative of this end node with respect to our target weight, right? Which is a partial Z N H over partial W and N H. Is that done? Not yet, right? We only finished the first pass, right? Remember, we have 3 passes, right? So the second pass, we're gonna follow the same procedure, right? So it's from what Y, Z0, and then ZNH. Right? Again, starting from Y, right? On Y, we always compute partial L over partial Y, right? And then from Y, go back to Z0, right? Look at the yellow pass, right? So the parent is Y, the child is Z0. So I'm going to compute partial Y over partial Z0, right? And then from Z0, we'll go back to ZNH, right? Remember, stick to the yellow pass. So then we compute partial Z0 over partial ZNH. And then finally, we'll multiply partial ZNH over partial W and NH. Right? So we finish computation for the second pass. Again, we just multiply the partial derivatives along that path. But that's yet finished because we have a third path, which is Y, Z1, and ZNH, right? But we follow pretty same computation, right? We just as partial L over partial Y when you starting from the output neuron, right? Then we go to Z1, then we compute the partial parent, which is Y over partial Z1, right? Then we'll go back to ZNH, compute the partial Z1 over partial ZNH. Then we'll multiply partial ZNH over partial W and NH. And we now finish processing all the passes, right? We just add them together, we get our final partial derivative with respect to W, M, and H. Is it clear? Mm-hmm. Yeah, you multiply the partial derivatives along each path, right? For one path, you got a multiplication, right? And also you need to multiply with partial Z and H over partial W, M, and H. That's just the one path result. Then you need to add another path result and third path result to get the final result. Yeah, yeah. You mean this one? This one? This one? So the GS actually is this guy. Right. Yeah, just stop at Z and H, right? Because you can see that because for every path you have to compute. Finally, you get back to Z and H. You have to compute partial Z and H over partial W, M, and H. It is a common factor. All right. So this guy is the same. They're all the same. Yes, for different paths actually. So if it sounds straightforward, everyone, I'm gonna move to next. Any other question? Like, this is just apply the graphical representation of the chain rule to do this. Faster. This one or this one? This one? GS? You mean you have a question on this? Okay, so which term are you? This one? This one? Oh, this is just the accumulator, right? You want to add them all together. You want to implement that. Okay, this is you can assume this is A equal to 0, right? And when you compute this guy, you add to A. When you compute this guy, you add to A. When you compute this guy, you add to A. Right? So you got some result, right? This one is actually a summation of those products, right? So you initialize them to be 0, right? In every iteration, you add up the new result until you add up all the products, right? So it's just you can build a pseudocode, right? Okay. Action doing this is pretty stupid. However, this is very, very important for us to motivate the real bipropagation step. So to do that, I have to do the tedious job again. I'm going to showcase you a more complete neural network, right? And apply this again and say why should we avoid this computation. So I'm gonna draw a 3-layer neural network. So this is why. Oops. So this input layer, so x0, x1, x2, right? So this is z0, z1, z2. So this is oh sorry, we should have the index of the layer, right? So this is z0, 2, z1, 2, and z2, 2, right? And of course, we have the output neuron. Let me make it more clear. So this is y, right? We have output neuron. You feed the output to the loss function, you got loss value, right? So suppose we want to compute some edge weight, right? It's here. So I'm gonna use another color to make it clear. Oh, gosh. So this is denoted by W111, right? So if we want to compute partial L over partial W111, how should we do? So following the protocol we just mentioned, we look at edge W111 stays, which is this edge, right? So this edge points to Z11, right? So this is target node. This edge points to, right? Then we'll look at all the paths from Z11 to the output neuron. How many passes does it have? 3, right? Because Z11 connects to all the neurons in layer 2. So actually I have 3 passes, right? So you have to enumerate all the passes, right? So let me mark them, right? This one, this first one, this is the second one, and this is a third one, right? So to compute that, we just need to go through every pass, right? Let us start from the left pass, which is the dark blue one, right? So starting from y, right? We know that we need to compute partial L over partial y. Then from y, go back. Let me use this color, partial L over partial y, right? We need when we go back from y to z02, the parent is y, the child is z02, right? We compute partial y over partial z02. Then we go back from z02 to z11, so get partial z02 over partial z11. And finally, we need to compute partial z11 over this edge weight, right? So it's partial z11 over partial edge weight w111, right? So this is just a finished one pass, right? So let us go to the next pass, which is the blue, which is the green one in the middle, right? So again, we begin at the output neuron y. So for that, we're going to compute the partial L over partial y again. And then we go back to z12, which means that we compute partial y over partial z12. Then we go back to z11, right? So compute partial z12 over partial z11. Then we'll multiply partial z11 over partial w111. This is the beginning node with respect to w111, right? So the second pass. So we just need to go through the remaining pass. The third pass, the white one, right? Again, we start from the neuron, output neuron, right? Which we're gonna compute partial L over partial Y. Then we go to Z22. That means we compute partial Y over partial Z22. And then we go back from Z22 to Z11. So we get partial Z22 over partial Z11. And finally, we compute partial Z11 over partial W111. Okay? So now we just follow the protocol, like this here, right, to compute this guy, right? So first, we found out because for every path, finally, we need to compute partial Z11 over the weight, right? They're a common factor. So let us just take them out, right? So we have this guy, adds them together. We actually don't need this factor, right? So now, let us look at the summation inside this big parenthesis. What does this summation mean? What can we observe from this summation? Can I say it again? Yes, exactly, right? So if you look at this summation, actually following the chain rule, right, from the graphical representation chain rule, it is exactly partial L over partial Z11, right? Neural network itself is a function dependency graph, right? So if you look at this summation, essentially is to find out the path from Z11 to Y, right? And over all the paths, we just multiply the partial derivative over all the paths and add them together, which end up with partial L over partial Z11, right? Does it make sense? So that means actually, if we know this is a partial L over partial Z11, we don't need to recompute it. So let's just assume that, okay, we have a computer that was catch that. So what if I want to compute another edge weight, right, pointing to Z11 as well, which is W211, right? So if we want to compute partial L over partial W211, how can we compute it? Right. So just copy this result here, right? Partial L over partial Z11, then multiply with partial Z11 over partial W211, right? You don't need to explicitly find out Z11 and how many passes from Z11 to the output neuron again, and then you enumerate all the passes and then multiply all the partial derivatives along every pass, add them together, right? Because they're just the result, partial L or partial Z11, we'll only need to calculate once, right? And actually, if we have such kind of observation, if you can catch them, we only compute it once. And for all the edge weights, right, on edges pointing to Z11, you just take out this common factor, partial L over partial Z11, then multiply with the partial derivative of Z11 over the over the edge weights. So this will save a lot of computation. Right? So if you follow this protocol, right, every time we apply the chain rule all the way up to the output neuron, you know, to compute this edge weight, this edge weight, and this edge weight, you'll compute the same intermediate results for 3 times. Right? However, if you just compute it once, you catch it, you know that it is actually partial L over partial Z11, which is the target node the edge points to. Right? You only need to compute once. Right? For the remaining, what you need to do is just to compute partial Z11 with respect to all the weights on edges connected to Z11. Right? So that will save a lot of computation. This is the key idea of back propagation. So what is back propagation? It will sequentially compute the partial derivatives of the loss with respect to every neuron in every layer. Then we will move back to one layer you're going to leverage the results from the previous layer to compute the partial derivative with respect to the current neurons in the current layer. And with the partial derivative with respect to all the neurons in the current layer, you can then straightforwardly compute partial derivative with respect to the edge weights connecting to the current neurons. So move it back to one layer back. You do it layer by layer until you arrive at the input layer. So this is the general idea. So does it make sense? Okay. And don't worry, we're gonna go through a very detailed example to showcase the computation procedure, and you'll get to the details, right? So, but here, general idea is that okay, to catch. The idea is to catch. How to catch that? We just need to catch all the partial derivatives with respect to the neurons of the previous layer. You see that it will be enough for us to compute the partial derivative with respect to neurons to the next layer. And once you get partial derivative with respect to all the neurons in the current layer, it is enough to compute the partial derivatives with respect to the weights on the edges pointing to the neurons in the current layer. So do it one by one until you reach to the bottom layer. Okay, so I'm gonna write this example again. So this is a output neuron Y. Is X0, X1, X2, which is input layer. Then the first layer, Z01, Z11, and Z21, and Z02, Z12, and Z22. Okay. So this is the layer 0, input layer, hidden layer 1, layer 2, and output layer is layer 3. So backpropagation, as the name suggested, will start from the output layer. Right? We're going to start from this output layer, that means layer 3. Right? So in each layer, we're going to compute the partial derivatives with respect to all the neurons in that layer, and also with respect to all the weights on edges pointing to the neurons in that layer. Right? So in the output layer, we only have one output neuron, which is Y, right? So our goal in the first step, right, is to compute partial L over partial Y, right? So only one neuron in that layer. And also the associated edge weights, right? So that means all the weights on the edges pointing to Y. So here it will be W01, 3, W113, and here is W 2, 1, 3. Remember, Y is indexed as 1. So that means with partial L or partial Y, we can compute partial L over partial W 013, partial L over partial W113, partial L over partial W213. Okay. So this guy is fairly easy to compute, right? Because we know that L is a direct function of Y, right? So you can just apply the function form of L to compute Y, right? If your L is a square loss, it's simply Y minus Y star, right? And then with partial L over partial Y, how do we compute the partial derivative with respect to weights on edges pointing to 1? We actually have done that. So it's pretty straightforward. We just multiply partial L over partial Y times partial Y over partial weight, right? Right? Remember this weight, W113 on the edge directly connecting to Y, right? So it only depends on Y. So what we need to do to compute the partial L over partial W113 is partial L over partial Y times partial Y over partial W113, right? Similarly, partial L over partial Y times partial Y over partial W213, right? Does it make sense? Okay. So this guy, the first factor is common factor, which has already been computed, right? We just read it. And what we need to do is just to compute the partial Y, the output neuron, with respect to the weights W013 here, W113, W213. Okay. And this computation is really relatively easy because Y equals to W013 times Z02, right? Plus W113 times Z12 plus W213 times Z22, right? It's a linear combination. Everyone's comfortable, right? Any question? Yeah, you can use dictionary. You can use follow. It doesn't matter. Yeah, what we need to do is just look at the step, every step, what do we do? And then you can try to organize them in whatever data structure you want. Okay, so the first step is pretty straightforward, right? So we finish computation of the partial derivative of loss with respect to the neuron Y, and also the partial derivative of loss with respect to all the weights, right? On the edges pointing to the neurons, like neuron Y, right? And then we move to the second layer. Move one layer back, which is layer 2, right? So our goal in the second layer is to compute partial derivative of loss with respect to all the neurons in that layer. Okay? So that amounts to partial L over partial Z02, partial L over partial Z12, partial L over partial Z22, right? And once we have that, we have these 3 results in our hand, then we can simply compute all the edge weights on the edges pointing to these 3 neurons, right? Which means the edge weight here, 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 a lot of, right? So let me just write it as partial LW, right? The target layer is 2 and M and N, right? So M, N, we just in 0, 1, 0, 1, 0, 1, 2, right? So let us look at how do we compute each neuron here, right? So how to compute partial L or partial Z02? I'll do that. No, not necessary. Yeah. Yes, exactly right. So if you will, L is a function of Y, right? So that means you can just compute partial L over partial Y, and then times partial Y over partial Z02, right? And similarly, we will compute partial L over partial Z12, it would be partial L over partial Y times partial Y over partial Z12, and partial L over partial Z22 equals to partial Y, L over partial Y times partial Y over partial Z22, right? And remember, all those computation require partial L or partial Y, which has already been computed in the previous step, right? So you don't need to recompute it. What you need to do is something brand new. You have to compute. You cannot avoid, which is partial Y over partial of every input neuron. Here is Z02, Z12, and Z22. Right? Does it make sense? Right? And once you got this guy, right? If you want to compute partial L over partial W to say any weight here, for example, if I want to compute this edge weight, which is W220, right? How to do that? How to do that? This edge weight points to Z22 only, right? So it only directly depends on Z02. So if you collapse L as a function of Z02, Z12, and Z22, you just will it in that way. So then partial L over partial W002 is simply partial L over partial Z02 times partial Z02 over partial W002, right? Remember, Z12 and Z22 has nothing to do with W002. It does not depend on W002 at all. And the good thing is that this guy has already been computed. You don't need to recompute it. And similarly, if you want to compute another edge weight, right? Say here, right? Edge weight here. So because it points to Z02 as well, you just read out this guy and then compute partial Z02 over this particular weight. This is fairly straightforward. And similar computation procedure applies to all the other weights, right? Say some weights here, like which is W2 and 22, right? If you want to compute partial L over partial W222, how do you do that? Which node it points to? This guy, right? So just read out partial L over partial Z22, then partial Z22 over partial W222, right? So this guy has already been computed, right? You don't need to recalculate. Just need to compute partial Z22 over partial W222, right? Right. This is essentially to view the whole loss function as collapsed as a function of Z02, Z12, and Z22, right? And then you take the partial derivative, you just need to take partial derivative over this neurons, and then take the partial derivative of those neurons with respect to the weights, right? And then we finish the computation of the step 2, that we got the partial derivative with respect to all the neurons and all the weights on edges pointing to these neurons. Right? Then in the third step, we move to layer 1, right? Where our goal is to compute, again, to compute the partial derivative of L with respect to every neuron in this layer. Of course, with those partial derivatives, it's straightforward to compute the partial derivative with respect to all the weights on the edges pointing to these neurons, right? So I'm going to use one quick example to show that, right? So how to compute partial L over partial Z11, like this guy. Let me use this. How to do that? How many parents does Z11 have? All neurons in layer 2 are parents of Z11, right? So that means Z11 depends on all the neurons in layer 2. Right? So then apply the chain rule. It is partial L over partial Z02 times partial Z02 over partial Z11 plus partial L over partial Z12 times partial Z12 or partial Z11, then partial L over partial Z22 times partial Z22 over partial Z11, right? And good thing is all these terms, partial L over partial Z02, partial L over partial Z12, and partial L over partial Z22 have already been computed in the second step. You just read it out. What you need to do is to compute each of the previous neuron Z11 connects to its partial derivative with respect to Z11, right? Which is partial Z02 with respect to Z11, partial Z12 with respect to Z11, and partial Z22 with respect to Z11. You just multiply them together, you get a result. Again, this comes from the fact that I collapse the function of the loss and view it as a function of Z02, Z12, and Z22. Right? And then I apply the chain rule. It's straightforward because Z11 are dependent on all the neurons in the second layer. So that's where we have to consider the partial derivatives with respect to all the neurons in the previous layer. And similarly, we can compute the partial derivative for Z02, Z22. With that, we can compute the partial derivative with respect to all the edge weight. Right? On the edges pointing to the 3 neurons in layer 1. Right? Then we finish computation. Right? And finally, we reach to the input layer. We finish the computation. So that is the propagation. So every time we compute the partial derivative of the loss with respect to the neurons in the current layer, using the result of the partial derivative with respect to the neurons from the previous layer, and then we catch them and utilize them to compute the partial derivative with respect to the associated weights, and then move to the one layer before, right? We move it back from the output layer until we reach to the input layer. Okay, let's stop here today. Right? On Thursday, we're going to go through this example in detail again, right, to strengthen your impression. Right? And I highly recommend you guys to manually follow this procedure myself. This is very important for you to implement your backpropagation algorithm. Right? If you don't understand the whole procedure, you won't be able to implement. Okay.